Okay, so now we're going to talk about some special factorizations that can be used as shortcuts when you're factoring polynomials. You will notice that these are pretty similar. In fact, they're kind of the reverse version of some of our special products that we talked about back in chapter 5. So from section 6.5 in our book, I'm just going to call this squares. So these are factorizations that involve squared terms. Okay, one of the most common and useful ones that you'll see is called a difference of squares. Okay, so these are when we have polynomials of the form a squared minus b squared. And if you remember, so from this is one of our factorization formulas. It's actually the reverse of the sum and difference, product formulas. So this actually factors out to be a plus b times a minus b. Because remember, when we FOILed out this side of it, the middle terms cancel out. We got a times a negative b plus a b times an a. Those are equal opposites. Cancel it out to 0. These are really common things to see in factoring. So a really typical example, you might see something like x squared minus 9. So it might help you at first to identify your a and your b, and then you'll see how to split up the factors. So here, the a is just going to be an x. So we have an x squared. That's our a. And then notice, okay, 9 is a perfect square. It's the square of 3. So then we have 3 squared. 3 is our b. And then we just write that. So we have a x plus b plus 3 times x minus 3. To make a plus b times a minus b. Okay. So that's your typical difference of squares. Just to see another example. So I would say go ahead and maybe pause the video after I write this and then try to work it on your own, and we'll go through it. So let's try something like 4y squared minus 144. Okay, so go ahead and pause, try to work that out. Right. So now we have a little bit more complication in our terms. We might have to, so we need to think about what would be the square root of each of these terms. That's going to be our a and our b. So maybe look that I could write this as 2y quantity squared, because a 2 squared is a 4, and then y squared is y squared. Okay, and then 144, that is 12 squared. Okay, so then a will be the 2y, b will be the 12. So then we can factor this out as, okay, a plus b, that's 2y plus 12. A minus b is 2y minus 12. Right. So that's the difference of squares factorization. And just to work one more in here, let's maybe do a third example. Let's throw something a little different in there. Let's do 9x squared minus, how about 25y squared? So go ahead and pause that. Try to work it out on your own. Okay, so maybe we start by noticing, okay, 9x squared, so that's going to be, if we squared 3x, that's what we would do. All right, and then 25y squared, so that would be the square of 5y. So in this case, our A is the 3x, our B is the 5y. So our factorization should be A plus B is 3x plus 5y. And then A minus B, 3x minus 5y. Okay. So that's difference of squares in several examples. All right. Now, a really easy one is called the sum of squares. And although a little bit less common, it's important to point this out because it's easy to confuse this with the difference of squares. So this will look a lot like a difference of squares. It's a squared plus b squared. What's tricky about this is this actually doesn't factor generally. So it is, I will say, prime. You may have a GCF in there, but after you get that out, it's going to be unfactorable, which means you're actually done. It's actually the easiest one to do. So prime after factoring the GCF. So do look for a GCF of terms, but if you have, once you get that out, if it's just something squared plus something squared, it's done. There's no more factoring. I'll just do a simple example here. So something like maybe, how about 4x squared? No, let's say 24x squared plus 6. So we would notice there's a GCF of 6 in both terms. So let's take the 6 out. That leaves us with 4x squared plus 1. So we've got all the common factors out. This is a perfect square term, as is the 1. But since they're added together, that's actually prime. And we're done. This is the factorization. Okay, so just keep an eye out. Make sure that you can tell the difference between the sum of squares and the difference of squares. That's what's really important. If there's a minus sign there, then you can factor it like we did with the first one. But if it's a plus, you're done. That's it. Okay. third one, that's probably a little high up there. Our third factorization. So these are the perfect square factorizations. We get 2 of those. And these are exactly like the perfect square multiplication formulas from chapter 5. So, but we're just turning them around. So, perfect squares. Okay. So one form that's a perfect square that we'll see is if we have a squared plus 2ab plus b squared. That factors to be, so the sign in the middle is always going to be the same as the middle term. This becomes a plus b quantity squared. Similar one is the perfect square of a difference. So a squared minus 2ab plus b squared, and that just equals a minus b squared. Okay, so these ones are a little harder to identify, but you'll start to recognize patterns with these. There are going to be certain perfect squares that come up all the time. So like things like x plus 2 squared, x plus 1 squared, x minus 3 squared. You'll learn to recognize what those look like when they're multiplied out, and then you'll be able to factor them really fast. Otherwise, our usual factoring methods will work. So you can still use the AC method. You can still use trial and error. And often the leading coefficient is 1, so it might even be easier than that. Let's take a look at a more kind of difficult example. Well, no, I'll start with an easy one. So let's do x squared minus 6x plus 9. And just look at how we can identify that this is actually a perfect square polynomial. So what this form is telling us is, okay, I want to look first at the first and the last terms and see that those are perfect squares themselves. So I'm going to look at the x and the 9. I should be able to rewrite those as, okay, x is the thing that's squared, and then the 9, okay, so that's 3 squared. So now can I write the middle term as 2 times x times 3? And yes, I could, right? 2 times 3 makes a 6. So we actually have here a minus. Let's get a little more space there. So minus 2 times 3 times x. And then as before, we have the 3 squared for the 9. So that tells us, so I've identified my perfect square terms, the a squared and the b squared. And then if I can write the middle term, if I can say pull out a 2, and then whatever's left is a times b, then I know I have a perfect square. So in this case, we got, so the minus 2, that's b times a, just because I wrote the x second. It's still the same thing as this one. So that tells us our factorization should be, so we have the minus sign, it's going to be a minus b squared. So x minus 3 all squared. So that's your basic perfect square. I generally wouldn't go to all that trouble to do it. I'm just going to default to the AC method. But like I said, this is one that you'll come to recognize as you do more of these problems. So let's do a couple more examples. All right, let's try 9x squared minus 12x plus 4. So maybe take a minute, pause, try to work this out. Okay. So going with our method of trying to figure out, based on the terms, if we have a perfect square, maybe we look at 9x squared and see, okay, that's the same as 3x all squared. All right, so that one's a perfect square. And 4, well, that's 2 squared. So it looks like we have our A and our B. So now let's think, can we write the middle term, if I take a 2 out, so that's going to be a minus 2. Okay, and then if I took a 2 out of 12x, let's get a little space here for this. So minus 12x equals minus 2 times 6x. Okay, and yeah, 6x we can see is the same as 3x times 2, right? Okay, so it looks like we do indeed have perfect square. Now we just want to write that. So that's our minus 2ab. Okay, so now we just want to write that as a perfect square. So that's going to be a is 3x minus b, which is 2. 3x minus 2 squared. Okay, and of course, we can always check this by using FOIL. So go ahead and 3x minus 2 times 3x minus 2. We get first times first, 9x squared. Outside, so outside terms gives us 3x times a negative 2. That's a negative 6x. Inside terms, negative 2 times 3x, another negative 6x. And then negative 2 times negative 2 is positive 4. And then if we simplify by combining the like terms, so we're going to combine our minus 6x, our minus 6x. We get 9x squared minus 12x plus 4. Back to the original. Okay. So this also points out a good thing. The reason that we have this 2 here is because we always, when we FOIL a perfect square, we double the middle. Like the outside and the inside are the same thing. So the 2 middle terms are going to be, we're going to get 2 of the same thing. And that's why the 2 comes out. It explains why we have the factoring formula the way we do, but also why the multiplication formula has the 2 there as well. All right, so that's it for our factoring methods with trinomials. Now we'll go and look at a couple of other ones with cubes.